Every year, more than 100 countries each send up to 6 of their brightest teenagers, or the occasional prepubescent prodigy, to represent them at the International Math Olympiad, commonly known as the IMO. The contest is essentially a test, spanning over 2 days, with 3 questions given over 4.5 hours each day. The questions are all proofs, meaning you don't simply find some numerical answer, you have to discover and articulate a rigorous line of reasoning to answer some difficult question. Then each one is scored on a scale from 0 up to 7. Each country has a different way of selecting its 6 contestants. In the United States, for example, it starts with a test called the American Mathematics Contest, or AMC, which any high school can choose to take part in, consisting of 25 questions given over 75 minutes. The top scorers in that are invited to take the American Invitational Math Exam, or AMY, consisting of 15 harder questions given over 3 hours. And the top scorers from that are invited to the USA Math Olympiad, which is structured just like the IMO. We have 2 days, each of them with 3 proof-based questions given over 4.5 hours. And then the top scorers from that are invited to a special summer training program, at the end of which 6 get selected to represent the country at the IMO. Of interest to us today is the 2011 IMO, where out of 563 total participants, representing 101 countries, there was that's interesting. All 3 of those are prime numbers. I wonder what the odds of that are. Yep, sorry, getting distracted. 563 students. There was only one, Lisa Sauermann from Germany, who got a perfect score. And the only thing standing between the next 2 runners-up and a perfect score was problem number 2. Well, okay, admittedly this is a slightly disingenuous way to introduce things. If you look at the full data, problem 6 was probably the real clincher. But I want to draw the spotlight on problem 2, because it's extremely beautiful, it's unexpectedly challenging, and yet the solution is very approachable. So let's pull it up and read through the thing carefully. Let S be a finite set of at least 2 points on the plane. Okay, so as you read the question, it's often helpful to start drawing out an example for yourself. Assume that no 3 points of S are collinear. In other words, you never have 3 points that line up. So you can probably predict that something in this problem will involve drawing lines in a way where 3 points on one line would mess things up. A windmill is a process that starts with a line L going through a single point P in S. The line rotates clockwise around the pivot P until the first time that it meets some other point belonging to S. Again, while we're reading, it's helpful to draw out an example. So we've got this line pivoting around some point until it hits another. This point, Q, takes over as the new pivot, and the line now rotates clockwise around Q until it next meets a point of S. This process goes on indefinitely. Alright, that's kind of fun. We keep rotating and changing the pivot, and you can see why they call it a windmill process, and you can also see why they specified that no 3 points lie on one line. You wouldn't want to run into the ambiguity where you don't know which pivot to switch to. Okay, so with all this set up, what's the question? Show that we can choose a point P in S and a line L going through P such that the resulting windmill uses each point of S as a pivot infinitely many times. Okay, there are 2 reasons I call this problem unusual. The first is that it doesn't exactly feel like a traditional math question, does it? Other Olympiad problems involve some function to analyze, or a numerical pattern to deduce, or maybe a difficult counting setup or an elaborate geometric construction. But this windmill question, well, it's more of a pure puzzle. And that's really its charm. Proving this fact, that some initial condition will result in a windmill hitting all points infinitely many times, well, that doesn't test your knowledge of a particular theorem, it tests if you can find a clever perspective. The spirit of the IMO is for success to feel like making 6 little discoveries, rather than recollecting 6 facts or 6 nifty tricks. So in that sense, the windmill puzzle is the perfect problem. It tests only insight, not memorized knowledge. But that blade cuts both ways. Whereas to prepare for other sorts of questions, you could imagine studying and practicing with the common results from one corner of math, what could possibly prepare you for answering a question like this? How do you systematically go about finding a clever perspective? And this brings us to the second unusual thing about this problem. Based on the results, I'm going to guess that it turned out to be a bit harder than the contest organizers expected. You see, typically the 3 problems of each day are supposed to get progressively harder. I mean, they're all hard, it's the IMO, but problems 1 and 4 should be relatively doable. Problems 2 and 5, well, they're challenging. And problems 3 and 6, they can be brutal. But take a look at how many of the 563 participants that year got perfect scores on each of the problems. Only 22 of them got a perfect score for this question number 2. But by contrast, 170 got a perfect score on problem 5, which is supposed to be about the same difficulty. And more than twice as many, 51, got a perfect score for problem 3, which is supposed to be harder. You might notice that only 6 students got full points on problem 6 that year, so by some measure that one is probably the hardest one on the test. But what's strange is that if you look at those 6 students, who are clearly phenomenal world-class problem solvers, this windmill puzzle evaded 5 out of 6 of them. But again, this problem is not hard because of the background knowledge it demands. It only asks for you to find the right vantage point. And what that means is that any one of you watching this video can understand the solution, and hopefully even feel like you could, with enough time, stumble across a solution like this yourself. The first step with any puzzle is simply to play around with it and get a feel for it. And it's always good to start with the simplest case and slowly get more complicated from there. The simplest case for our windmill problem is when there are 2 points, where the line basically trades off between each point as a pivot. So that works well enough. And if you add a 3rd point, it's pretty clear that the line will just rotate around them. It might not be entirely clear how you would phrase that as a rigorous proof yet, but right now you're just getting a feel for things. You want to believe the result before you prove it. Adding a 4th point is where it gets interesting. In some places, your windmill will go around the 4 points just like it did with the triangle, but if we put it inside the other 3 points, then it looks like our windmill never hits it. And looking back at the problem, it's asking you to show that for some starting position of the line, not any position, the process will hit all the points infinitely many times. So for an example like this, where there's potential trouble, what happens if you start with a line going through that troublesome middle point? Again, at this point, we're just playing around, maybe moving your pencil among dots that you've drawn on scratch paper. Questions of rigor and proof are going to come later. Here, what you'd see is that your windmill does indeed bounce off all the points as it goes through a cycle, and it ends up back where it started. But would that continue as you get an arbitrarily complicated set of points? The worry you might have is that for some very large sets where some of the points are sort of inside the others, you might be able to start off with the line somewhere in the middle, but that maybe this windmill process ultimately takes it to the outside, where it's going to be blocked off from those inner points. If you were to play around with this, and mind you, it can take some meaningful time to draw out the examples and think it through, you might notice that when the line starts off passing through the middle of your points, it tends to stay there. It never seems to venture off to the outside. But can you guarantee that that will always happen? Or rather, can you first make this idea of starting off in the middle a little bit more rigorous, and then from there prove that all of the points will be hit infinitely many times? And as a general problem-solving tip, whenever you have a vague idea that feels productive, try to work on a way to make that idea more exact, preferably putting numbers into it. And then ask questions about those numbers and see where it takes you. In our example, one way that you could formalize the idea of it passing through the middle is to count how many points are on either side of the line. If you give the line some orientation, you can reasonably talk about a left half of the plane, say coloring all of the points to the left of it blue, and a right half of the plane, say coloring all of the points to the right brown. And what it means for the line to be in the middle is that there are as many blue points in our set as there are brown points. For the moment, let's say that the total number of points is an odd number, and let's color the point that the line passes through white, sort of a neutral color. So for example, if there were 11 points, then you would have 5 blue ones to the left of the line, 5 brown points to the right of the line, and 1 white one that is passing through. The case with an even number of points will be similar, just slightly less symmetric. These numbers give us a new question to ask. What happens to the number of blue points and the number of brown points as this process plays out? In the example shown, you might notice that as the windmill proceeds, those numbers are always 5 and 5, they never change. And if you were to play around with other examples, what you'd find is that the same is true. the number of points on a given side of the line seems to stay constant. If you're feeling active, take a moment and pause to see if you can think through why that would be true. Well, the key is to think through what happens as the line changes its pivot. Having given the line an orientation, we can talk reasonably about which half of it is above the pivot and which one is below. So if the line hits a blue point on the left, it must happen below the pivot. And so as it changes pivots and continues rotating clockwise, that old pivot, which is now above the new one, ends up to the left of the line, in the blue region. And entirely symmetrically, when it hits a brown point, it all happens above the pivot, meaning that the old pivot ends up in the brown region on the right. So no matter what, the number of points on a given side of the line, that cannot change. When you lose a blue point, you gain a new one. When you lose a brown point, you gain a new one. Great! That fact is our first key insight. So why would this imply that the line must hit every point infinitely many times, no matter what weird set of points you dream up? Think about letting this process go on until it's turned 180 degrees around. That means that it's parallel to the starting position, and because it has to remain the case that half the points are on one side and half the points are on the other, it must be passing through the same point that it started on. I mean, think about it. Otherwise, if it ended up on some other point, it would change the number on a given side. Additionally, since the line has rotated halfway around, everything that was blue has become brown, and everything which was brown has become blue. And the only way that one of these points can change colors is if it got hit by the line at some point during the process. So, for our odd-numbered case, that means that after a half rotation, the line is back to where it started, having hit all of the other points. What that means is as time moves forward, it repeats exactly the same motions over and over, hitting all those points infinitely many times. So what about the other case, when there's an even number of points? We need to alter the scheme, but only slightly. Let's say that in that case, so that we can have the same number of blues and browns, the pivot counts as a brown point. So now we say select an initial point so that half of the points are blue, meaning all are on the left, and half of them are brown, which now means they're either on the right or the pivot. Just as before, after a 180-degree turn, all of the points will have swapped colors. Except this time, the line will be passing through a different point after the first half turn, specifically one that used to be blue. But after another 180 degrees, that line must be passing through the same point that it started on. Why? Again, it must be parallel to the starting position, and if it was anywhere else, the number of points on a given side would be different, which we know can't happen. So once again, we have a cycle that hits all of the points and which ends on the same position where it started. This time it takes 360 degrees. But that doesn't matter, it still means that all points are hit infinitely many times as this process proceeds indefinitely.